So here we have a Python example to demonstrate the mu law companding. So here I'm importing libraries we're going to use. We're using NumPy and pyplot. Here I'm defining some signal process parameters. So we're going to use a sampling frequency of 32 kilohertz. And here we are defining the signal to be quantized. So it's the same signal that we used before when we explored the mid-thread and mid-riser quantizer. So it's a signal. The signal is a sine wave with amplitude equals to 1, so it goes from -1 to 1 and a frequency of 500 hertz. And here we are doing dequantization, and the dequantization, so we have a number of bits equals to 4, so we calculate the step size. So here now it comes the compression. So we're applying this formula that we calculated here. So we're doing this compression, so it's this formula here. So we are doing this formula here, which is defined here. Then we are doing the quantization here, so we can see there is the mid-thread and mid-rise. Here we are doing the dequantization, so also for mid-thread and mid-rise. And here we are doing the expansion. So we are doing the expansion for the mid-rise and the mid-thread. So here we're just shaping everything to plot. So in case we want to plot more than one period, we can just change this period value that's defined here. So it's defined as I want to plot one period, but we can also plot more periods. And here is the quantization error, which is the quantized minus the original signal. And here we are plotting our signal and the quantized signal. So we can see that in blue we have our original signal, it's a sine wave, and we see that for the step size they are no longer uniform. So we have larger step size for larger values, and then we have smaller step size for small values. And here we have the quantization error. And like before, we can also listen. So this is the original signal. Here's the quantized, the mid-thread with the mu law companding. And here's the quantized mid-rise, also with this companding. And like before, we can also see these in the frequency domain. So we have our original, but then when it's quantized, we have this quantization noise here. So we have a different harmonics that are not present in the original signal. So due to quantization errors, we get this quantization noise. So what we have here then is an example. Yeah, we are using this compression and then this expansion. So this defines the companding. Yeah, in this case, the signal, it goes from -1 to 1, so there is no need for a normalization here. Yeah, but we can, for example, change here. Let's see, see 2 periods instead of just 1, and then we have our plot. Now we have 2 periods, and we still can see the effects of companding. So we have differences in non-uniform quantization. We have like smaller step sizes for small values and larger step size for larger values. Finally, what we will do now is a real-time mu law quantization, a Python example. So it's the same like we did before with mid-thread and mid-riser, but now we are including here a control for the mu law. So when we press this button here, then there will be the compression and expansion. So here now another difference is here that we are normalizing. So PyAudio is using 16-bit audio, So we are normalizing, so the values go from -1 to 1 instead of from -2 to the power of 15 to 2 to the power of 15. Here, when the mu law is on, so if we press this checkbox here, if we select this checkbox, then there will be this compression here. Then we have a mid-thread or the mid-rise, so we can also select here from this box mid-thread or mid-rise. Then we will have the expansion, so after the dequantization we have the expansion, and then we need to bring back our signal that is now from -1 to 1, bring back to 16 bits, so it goes from -2 to the power of 15 to 2 to the power of 15. So let's do this test. Like before, we could see that when we used the mid-thread with low bit depth, so a low bit accuracy, like for example 4, we've seen that the mid-thread was swallowing the small values, but then we will see that with this companding we will see what happens. So let's go for this example. Alô som, alô som, alô som, ei teste, 1 2, alô som, teste, ei teste, ei alô. So we see in action, yeah, that there is this compression and expansion, so this companding, and we get different results if we use just the mid-thread or the mid-rise quantizers, but introducing this companding, we achieve a different result.